Let's talk about the basics of solving exponential and logarithmic equations. So the first way we're going to solve exponential and logarithmic equations is through using the one-to-one properties. So these one-to-one properties are whenever the relationship is obvious. So like if I say something like 2 to the x power is equal to 2 to the 12th power, well, that's going to tell you that that's implying that x is equal to 12, because you know the only way a base 2 number can equal another base 2 number is if the powers are the same. So in this case, x would have to equal 12. Okay, so to show you some problems based off of that concept. If I say 5 to the 3x plus 2 power for this exponential function is equal to the exponential function 5 to the x minus 7. Well, the only way that the left-hand side could equal the right-hand side are if those two exponents are the same. So it's a simple linear equation. I just say 3x plus 2 must equal x minus 7. So then what I did is I got my x's on the same side, subtract x on each side to get 2x on the left. Get the constants on the same side, so subtract 2 on each side. Negative 7 minus 2 is negative 9. So we know 2x has to equal negative 9, thus x is going to equal negative 9 over 2. You never really have to worry about the answer you get to any exponential equation, and remember the reason for that is because the domain of any exponential equation is always all real numbers. So whatever answer you get, as long as your algebra is correct, it's a correct answer. Now, the next one here, I have the exponential equation 10 to the x squared plus 4x power, and I have that set equal to 1 over 1,000. So in order to think about this one, I need to get that exponential base 10 on both sides. I recognize 1,000, it's just 10 to the third power, but I know that it's in the denominator. So that means 1 over 10 to the third is the same thing as 10 to the negative third power. That allows me to see that this exponent has to equal this exponent. So I get x squared plus 4x has to equal negative 3. I move the negative 3 over to the left-hand side, and I get x squared plus 4x plus 3 is equal to 0. Whenever you have a polynomial set equal to 0, you factor the polynomial whenever possible. Certainly possible here. Factors of 3 that sum to get to 4, 3 and 1. Left-hand side factors to be x plus 3 times x plus 1, set equal to 0. Set each of your factors equal to 0 to solve for the values of x that satisfy this original condition. And there's two answers, x equals negative 1 and x equals 3 when these factors equal 0. So this one, unlike the first one that just had one solution because our exponents were linear, since I had a quadratic exponent, I expected two answers and I got them. The next one, I'm expecting one answer because now the exponents are back to linear. But before I try to do this one, it's the most complicated one in trying to get the common base on each side. Because it's not easy to get 81 to have a base of 27. So rather than even try to do that, I say, hey, 81 is a multiple of 27 times 3. How about I get these numbers to be both numbers base 3? And I say, well, 27 is just 3 to the third power. 3 times 3 times 3 is 27. 81 is one more power of 3, so it's going to be 3 to the fourth power. So I rewrite each of my exponential bases, 27 and 81, as 3 to the third and 3 to the fourth. Now I use my properties of exponents. Anytime you have a power to a power, you multiply. So the left-hand side is just 3 to the 12x minus 3 power. The right-hand side is going to be 3 to the 8x power. Now I know as soon as I get my exponential bases to be the same, I can set the exponents equal to one another. So 12x minus 3 is equal to 8x. Subtract out 8x on each side, you get 4x is equal to positive 3 when you move the negative 3 to the right. X is equal to 3/4. Pretty straightforward. Now, that same idea of the one-to-one properties not only can be used for exponential functions, it can be used for log functions too. So, for example, if I say the log base a of x is equal to the log base a of b, the only way that that could ever be true, since they're both the same base on the log, is what's inside would have to be the same. So that would imply that x is equal to b. So for my equation here, I'm wanting you to solve natural log. Remember, that's log base e. Everything in this problem is log base e. I have the natural log of x plus 13 minus the natural log of 4 is equal to the natural log of 3x minus 5. How can the left-hand side equal the right-hand side? Before you can even think about this problem, and I put it as a hint over here, but not only is it a hint, you can't work the problem without thinking about this. You're going to have to use our properties of logarithms to condense the left side of the equation first before trying to use your one-to-one properties to simplify. So I know anytime I have a subtraction of two separate logarithms, I can condense those to one logarithm and say the term that was inside the positive log has a factor in the numerator of that term, x plus 13, and I'll be dividing that by the 4 since that natural log of 4 was subtracted. So my condensed log that's equivalent to that is the natural log of x plus 13 over 4. Now, I just have that equal to the right-hand side, the natural log of 3x minus 5. The instant you do that, though, you say, well, the only way two natural logs can equal one another is if what's inside is equal to one another. So I ignore the natural logs and set the interior portions equal. From this step to the next, I didn't like that 4 in the denominator, so I multiplied by 4 on both sides. When I multiplied by 4 on the right-hand side, I had 12x minus 20. Then I got the x on the same side, so 12x minus x is 11x. Get the constant on the same side. Add 20 to both sides, you get a 33 on the left. So now if 11x is equal to 33, you divide by 11, you get your x equals 3. Now, in a log equation, you really should check that answer because we know that the domain of a logarithm, the term inside of a logarithm must be positive. So if that 3 caused any negatives or zeros inside of a logarithm, it could not be an answer. But it's not going to be a problem. It would be the natural log of 16 here, and it'd be the natural log of 4 over here. No problem. So that is our solution. But you should have thought about, could that be a solution? And the way we answered the question, if it causes a negative or a zero in any of those, it'd have to be discarded and called an extraneous solution. But in this case, no problem. Next type of problems, I want to look at solving exponential equations that you can't just use that one-to-one property. What if I can't make my bases equal to the same term? I'm going to have to do some other strategies. And the strategies that you're going to use, it's the whole concept of an inverse. The inverse of every single exponential function in existence is the logarithm of that same base. So if I have exponential function base a to the x equals b, how do I get rid of exponential base a? Well, I take the log base a of both sides of my equation. Log base a, exponential base a goes away, and you just have an x on the left-hand side. Your right-hand side is going to be whatever the log base a of b is equal to, and we'll have our calculator to simplify out that side of the equation. Okay, let's see this in action. So my first problem, and keep in mind these problems I will always want an exact answer, and then we'll use our calculator to get the decimal approximation. So if we have the exponential equation 4 raised to the 3x minus 5 power is equal to 230, then the first thing you need to do is say I need to get rid of that exponential base 4. How do we do that? You take log base 4. I take log base 4 of the function on the left, take log base 4 of the term on the right. And then I can say log base 4, exponential base 4 are inverse functions, just like I did up here. The log base a, exponential base a cancel. Log base 4, exponential base 4 cancel. And I just have 3x minus 5 remaining. Keep in mind, that's no longer an exponent. The exponential base canceled out, which means 3x minus 5. That's just a polynomial function now. That's going to equal the log base 4 of 230, which, using your change of base formula, that's equal to the natural log of 230 divided by the natural log of 4. Now, I'll solve for x. You say, well, you can solve for x by adding 5 to both sides. That's what I did here. 3x is equal to this quotient of natural logs plus 5. And then you can say, well, if 3x is equal to that, then x is equal to this expression divided by 3. And I would want this exact expression. The exact expression for x is the natural log of 230 over the natural log of 4 plus 5 all over 3. Now, to show you how you would calculate that using your calculator, you'd just say, so home screen here, I will put a fraction, alpha y equals, enter. And I even have a fraction inside the fraction, so I'll do that again. My first term is the natural log of 230. I'll close off that natural log. And we're dividing that by the natural log of 4. Natural log of 4. We're adding 5 to that fraction, and then we're dividing everything by 3. This should give me that 2.9742 rounded to 4 decimal places. And it does. So you're like, okay, no problem. Next one. The next one, I'm giving you an exponential function base e. But now, unlike the first one where the very first step, I could get rid of that I could get rid of that exponential base 4 by taking log base 4. Well, that's because the exponential function was by itself. If the exponential function isn't by itself, the first step is to get it by itself. So I have this exponential function over here. I first need to get it by itself. I'll subtract 6 on each side. So I get 2 times e to the x over 3 is equal to 24 minus 6, 18. Then the exponential function can be gotten by itself by dividing both sides by 2. That gives me 18 over 2 is 9 is equal to my exponential function. Now I need to get rid of exponential base e. Well, the inverse of exponential base e is a log base e, which is better written as a natural log. We take the natural log of both sides. Natural log and e eliminate one another, and so you just have x over 3 on the left. Natural log of 9 can't really simplify unless you want an irrational number. So I have x over 3 is equal to the natural log of 9. X is going to equal 3 times the natural log of 9. That's my exact answer. My decimal approximation of that, I just say 3 natural log of 9. And you can see we get here the 6.5917 rounded answer. Now for my next one, I have the exponential function within a rational, or I should just say a fractional expression. So I know I can't ever solve for a variable as long as that variable is in the denominator. Impossible. So even worse, it's in the exponent in the term within a denominator. So I can just say, okay, get it out of the denominator. How do I do that? Multiply by the denominator on both sides of my equation. When I do that to the left-hand side, I just get 1500. My right-hand side is going to be 200 times that denominator of 20 minus 5e to the 0.1x. So then I need to get this exponential function by itself. Let's get rid of the 200 multiplying it. I divide both sides by 200. 1500 divided by 200 just reduces down to 15 over 2. And I know 15 over 2 is 7.5. Now, on the right-hand side, I almost accidentally put 200 there, but I just have 20 minus 5e to the 0.1x left over. Then you can say, well, how do I get the exponential function by itself? I need to get rid of that 20. How do I do that? I subtract 20 on both sides. That's what I did right here. 7.5 minus 20, and the 7.5 was the 15 over 2, minus 20 should equal a negative 5e to the 0.1x. 7.5 minus 20 is just a negative 12.5. I divide that by negative 5, and again, you think, why did you divide by negative 5? Because that was negative 5 times the exponential function. The opposite of multiplication is division, so I needed to divide by negative 5 on both sides to get that exponential function all by itself. So now I know e to the 0.1x power is equal to negative 12.5 divided by negative 5. It's just a positive 2.5. Now I came up here and solved out my problem. I said I need to get rid of an exponential base e. How do I do that? I take the natural log of both sides. The inverse of an exponential base e is a natural log. So then I can say, well, the natural log of 2.5, natural log and e cancel each other out, and I just have the 0.1x remaining on the right-hand side. So if 0.1x is equal to the natural log of 5, x is equal to the natural log of 5 divided by 0.1. This would be my exact answer. My decimal approximation here, I would just go in and say, well, it's the natural log of 2.5. I'll close that natural log off, divide by 0.1. And you see where I got my answer, the 9.16 29 rounded to 4 decimal places. So now this page all talks about finding the solution to exponential functions. You'll notice once I got my answer, I circled it, whether it was exact or decimal approximation. I never wondered about whether the answer was actually an answer. That's because the domain of exponential functions is all real numbers. Any answer you get through legitimate algebra is a correct answer. The same cannot be said for logarithms. Remember, logarithms have a restricted domain. Whatever's inside the logarithm can only be a positive number. It can't even be 0. So we're going to have to check our answers on this page. But the basic premises of how we solve a logarithmic equation, it's the same as the exponentials. You're going to get the log function by itself, then you take the inverse of it on both sides to get rid of it. The inverse of a log base a of x is an exponential base a of x. So we exponentiate both sides of the equation to cancel out the log function. So if I have an equation that has a log base a of x and I'm trying to get rid of that log base a, I say, well, the inverse is an exponential base a. So I literally have to take each side of my equation and shove it up into the exponent of an a. So I get a raised to the log base a of x and a raised to the b power. And then exponential base a, log base a, they are inverse functions. I can eliminate them in that step. So now my left-hand side, a to the log a cancels, and I'm just left with the x in there. The term inside the logarithm is the only term remaining on the left. Well, your other side, you had to exponentiate it with an exponential base a as well. So it's just going to be whatever a to the b power is. And normally we'll be able to get whatever answer that's equal to, because we'll have numbers in there for the a and the b. Now, what I was saying earlier on this page, unlike exponential functions, you're always going to have to check for extraneous answers. Whenever we do logarithms, it's quite possible that you'll get an answer that you have arrived at correctly through algebra, but cannot be part of the original equation because it causes your logarithm to not exist. Let's take a look. Starting off with the first one here, pretty basic. You're like, well, why is this one basic? Because you already have the logarithm all by itself in the very beginning. Natural log of 2x plus 5 is equal to 4. How do you solve for x here? You get rid of the natural log. How do you get rid of a natural log? You do the exponential inverse of that. The exponential inverse is exponential base e. I have to exponentiate each side of my equation into the exponent of an e. And I really need to emphasize that here because so often I will see students think, oh, I just multiply by e on each side. That's terrible. That right-hand side is not e times 4 or 4 times e. It's e to the 4th power. The inverse of an exponential base e is of a log base e is an exponential base e. You can't have an exponential base e unless you put this entire left-hand side into the exponent of an e, which is why I have to do the same thing on the right-hand side. So both sides become the exponent of an exponential base e. Now on the left-hand side, though, it simplifies because exponential base e, log base e are inverse functions. They cancel. I just have 2x plus 5 is equal e to the 4th power. I want to get an exact answer, so I cannot evaluate e to the 4th power yet. I solve for x. Subtract 5 on each side. 2x is equal to e to the 4th minus 5. Thus, x is going to equal e to the 4th minus 5 over 2. That is your exact answer. Now, your decimal approximation to that, I can say, well, okay, it's going to be a fraction, and I'll have e to the 4th. The best way to locate e is its second natural log. And I'll say I have e to the 4th power minus 5. We're dividing that by 2. This should be the 24.7991 answer. Ooh, I'm in fractional form. Let me change my mode to where I'll get decimals. So now I'll go in, second enter, and I get the nice decimal there. I prefer a decimal to a fraction in this case. So 24.7991 rounded to 4 decimal places. Okay, now, good answer here. Now, why am I not even worried about that answer? Because I can just look at it and say, is that going to cause the inside of this logarithm to be 0 or negative. No, it's going to be a very positive number, even greater than 100. So it's going to be fine. I'm not worried about that answer at all. It's correct. Now, if you wanted to, though, so anytime you want to check your answer, it's pretty easy here. We know that this is the answer for x. All you would have to do is store that answer in as x on your calculator. And now watch, I'll type the left-hand side. The natural log of 2x plus 5. This answer better be 4, or you know you're wrong. But it is, so you know you're right. Gorgeous. Now, the next problem here. This one's more complicated than the last, because the last one, I could just go ahead and exponentiate base e in the very first step. You cannot do that here because you have two separate logarithms. The absolute first thing in these problems is you must get a logarithm by itself on a side before you can exponentiate. So I can say, well, okay, I can get a logarithm by itself by condensing the logarithms on the left. Anytime you have a minus, that tells you that the term inside of that logarithm belongs in the denominator. So I get the log base 2 of x plus 9 over x minus 5 on the left. That's set equal to 3. In order to get rid of log base 2, you exponentiate with an exponential base 2. So both sides of the equation go into the exponent of a 2. I have exponential base 2, log base 2. Those are inverse functions. They cancel. Your left-hand side is just going to be x plus 9 over x minus 5. Your right-hand side was 2 raised to the third power, since this side had to go into the exponent of a 2 as well. Obviously, those don't cancel, but you can evaluate. 2 raised to the third power is 8. So now I have this equation. In order to solve it, I multiplied by x minus 5 on each side. That gave me x plus 9 is equal to 8 times x minus 5. I distributed the 8 to get 8x minus 40. Then I said, well, let's get our x's on the same side. I subtracted x on each side. 8x minus x is 7x. Let's add 40 to both sides. 9 plus 40 is 49. I get 7x is equal to 49, thus x is equal to 7. And again, I'm confident that that's an answer because it doesn't cause any negatives within the logarithms. So I would just say that is a good solution there. The last one. Here's one where we are going to have an extraneous value. Like in the last one, I said I wasn't worried about the 7 because it would cause positives in both of those logarithms. Thus, it was a solution. This one, similar to the last one, you have to condense first. This time, both logs are positive, so both terms are multiplied within the numerator of this common log base 10. Remember, when you don't see a base, it's automatically base 10. So I have log base 10 of x times x minus 3 after I condense. My right-hand side is just a 1. Then you can say, I need to get rid of log base 10. How do I do that? I exponentiate both sides of my equation with an exponential base 10. 10 to the log base 10 of x times x minus 3. 10 and log 10 are inverse functions. Your left-hand side is just x times x minus 3. Your right-hand side was 10 to the first, which is 10. Then on your left, you can say, well, it's not helpful to have those factored out because it's only helpful to have factors if it's set equal to 0. So I go ahead and I multiply them, and I'm going to move the 10 over and then set it equal to 0. So I get x squared minus 3x minus 10 is set equal to 0. Then you just say, well, I'm trying to find factors of negative 10 that sum to get to negative 3. And that's negative 5 and positive 2. This factors to be x minus 5, x plus 2. We set each of those factors equal to 0. If x minus 5 is equal to 0, you know your solution is x equals 5. If x plus 2 is equal to 0, you know your solution would be x equals negative 2. Now, why did I circle the x equals negative 5 and restrict the x equals negative 2? It's not automatically. You don't just ignore any negative answers. But you look at the answers and you say, well, would that cause any zeros or negatives within the original logarithms? The 5 is fine. I'd have the log of 5 and the log of 2. No problem. Both of those exist. That is an answer. What about the negative 2? It can't, because actually in both of them it causes a negative. You'd have the log base 10 of negative 2 and the log base 10 of negative 5. You can never, ever have a negative number or a 0 inside of a log. that automatically causes an extraneous value. So it's a value that you arrive at through correct algebra that is not part of the domain of the original problem. So you say that cannot be an answer, extraneous. Our only answer is x equals 5. Gorgeous section here, guys. Now we'll be expanding our ability to do equations with these logarithms and exponentials in 4.6. It's really just a continuation of 4.5, but we'll be doing a lot more fun problems. So make sure you get the basics down in 4.5 before we move on to the next section. If you have any questions over this, please let me know.